Okay, in this presentation we are going to look at the negative binomial distribution. Suppose that we have a random variable x that follows the negative binomial distribution, and we have the following pieces of information. The probability of x equal to 0 is 0.2397. The probability of x equal to 1 equals 0.1039, and the probability of x equal to 2 is 0.0398. Okay? The question we're asked is determine the mean and the variance of x. Okay, so straightforward enough so far. Now, what we're going to do here is just actually remark upon the probability mass function. Okay, now there are multiple ways of stating the probability mass function of the negative binomial distribution, and in this particular instance we're going to go with the sort of default one. Now there are other variations of this, but this is what we will be looking at. Okay. So just to backtrack a bit, the R usually refers to the number of successes, K usually refers to the number of failures, and P is the number of the probability of a success, and that's the probability mass function. Now, I'm not good. That sort of suggests we're going to use the applications of the negative binomial distribution. Not in this particular video. What I'm going to focus on is the sort of mathematics of this expression here and getting ratios. Okay. Also, I should remark that there are different approaches here to doing this very same problem. I'm actually going to do it from this particular approach, but there is another approach which is well known to be associated with the negative binomial distribution, the AB0 thing. I'm going to sort of keep that aside because it's good to do it both ways, and in this way I'm going to use this approach. Okay, now, so this is a probability mass function here, and in particular we're interested in the coefficients of k. So here we have the probability of x equal to k. The binomial coefficients involving k, I should say. Okay, I just paused there for a second and reset. So the question is, what we're going to do is calculate or derive an expression for the probability of x equal to k plus 1 based on that probability mass function, which is denominated in terms of probability of x equal to k. So probability of x equal to k is what we have there, and what we want is the probability of x equal to k plus 1. So first off, let's look at the coefficients, the binomial coefficients. So the upper number, k plus r minus 1. So if we change k to k plus 1, we would get k plus r there. Likewise down here, if we change k to k plus 1, straightforward enough in that case, we have 1 minus p to the power of r. In that case, it's no change, and p to the power of k becomes p to the power of k plus 1. So what we want here is the ratio of probability of x equal to k plus 1 divided by the probability of x equal to k. That will give us an approach that we can use. So this part here is straightforward enough. The ratios. Just to sort of highlight one thing, that this part here is common to the numerator and the denominator, so that goes. Okay, so that's not involved anymore. So that expression is just times 1. Okay, this expression here, the probability of the p to the power of k plus 1 divided by the probability of p to the k, that just becomes p. Okay? So the binomial coefficients, the ratio of those binomial coefficients is what is interesting here. It's essentially the crux of the question, how to deal with these things. So what I'm going to do actually is just going to take a moment to write them all out. So the first binomial coefficient is k plus r factorial divided by k plus 1 factorial times r minus 1. So that corresponds to the first binomial coefficient, which is this one here. Okay, that's that binomial coefficient. Now what we're going to do is look at the second binomial coefficient, which is the one just below it, this one here, and I'm going to write that one out as well. Let's do this one in blue. So we have k plus r minus 1 factorial divided by k factorial times r minus 1 factorial. Okay, now that's a fraction. Immediately we can see that the r minus 1 terms will cancel out. So what we're left with is essentially a fraction divided by another fraction. So we have the numerators here, and I'm going to divide those, and the denominators, I'm just going to divide those to keep it simple, okay? So the denominators are down here. That's the denominator 1, the first denominator, and the second denominator. And the numerators are here. So just to sort of be very thorough about what I'm doing. Okay, so that's it really. So the ratio term for the numerators, which is k plus r factorial divided by k plus r minus 1 factorial, that simply is k plus r. Okay, I'll let you just check that yourselves. You should be fairly good with binomial coefficients and factorials. If you're not, yeah, that's not good. You should really check that stuff out first. So that should be straightforward enough. I just realized that I'd done the denominator ratios in a slightly confusing way that's not consistent with what I'd done with the numerators. But anyway, so when we looked at the previous page here, we had in the blue parts, we had k plus 1 factorial divided by k factorial, and the ratio of that is k plus 1. So essentially, the ratio becomes, the overall ratio is k plus r divided by k plus 1 times p. Okay? So that's the ratio of the numerators, that's the ratio of the denominators. We divide one by the other, k plus r divided by k plus 1, and remember we had p there also, which is p to the power of k plus 1 divided by p to the power of k. So now we're able to figure out use the numbers that were given at the start and try and figure out what we need to do. So in the first case, we're going to calculate the ratio of the probability of x equals 1 divided by the probability of x equals 0. And in this case, k is going to be 0. Okay, so that means our ratio is k plus r is 0 plus r divided by k plus 1, 0 plus 1, which is simply r. So this is r times p. So the probability of x equal 1 divided by the probability of x equal 0, that is 0.1038878 divided by 0.2397410. That works out to be 0.4333. Okay, so that's r times p. That is our first, that helps us start off. In the second instance, we have the ratio of probability of x equal 2 divided by the probability of x equal 1, 0.0398236 divided by 0.1038878. That works out to be 0.38333. Now, in this case, k is equal to 1. Okay? So if k is equal to 1, that means numerator on this expression here is r plus 1, and below it's 1 plus 1. Okay? So that is 1 plus r divided by 2 times p. So that's that expression there. Now, solving for r, what we have to do is solve for r. So what I'm going to do here is divide one by the other. Okay, so this is the first ratio above, and I'm going to divide it by the second ratio. Okay, a little bit confusing, but just to remark that this does make sense. Essentially what we're going to do is divide one number by the other, and just remember the p terms cancel out, okay, when we're doing this particular calculation. So 1 plus r divided by 2r, that is 0.38333 divided by 0.433, and that is equal to 0.88461. Okay, so little bit of working this out. Multiply both sides by 2r. 1 plus r equals 0.88461 times 2r, which is 1.7692 times r. Okay, so that means, since you're working it out, a bit of calculator work and a bit of algebraic operations, you should find that r is equal to 1.3. That means P is a straightforward enough job. 0.433 equals P times R, which is 1.3 times P, or R times P equals 1.3 times P, and should be able to figure that out. That means the P equals 0.33. So that's it done. Now there's other approaches to solving this problem, but you know, this is a sort of worthwhile getting the hang of it there, just making sure that you can work with binomial coefficients like that stuff there. I know that's a bit messy, but that's really where you need to be at with these videos, okay, or these exercises. Okay, leave it there.